right, good morning. Welcome to the start of week 4. Just a reminder, quiz this coming Wednesday, information for which is on the website if you haven't seen it already. Hopefully by now, all of you have solved your game of 15. Well, if not, we'll be focusing on that Friday onward in this class. A couple of announcements. The first from HCS, who, with our continued partnership, will be offering you guys a couple of more seminars coming up. Josh?
Hey guys, just out of curiosity, how many people came to the seminars on Linux and Unix? Okay, a fair number. I think we had probably about 40 in total. So we're going to continue offering seminars this week. Post your quiz. We're going to do 2 seminars on some text editors, lest you want to learn to use something a little more powerful than Nano. I'll be giving one on the wonderful world of Emacs this Wednesday at 3, and at 3:30. And then our president, expert on Vim and general smart person, Grant Dasher, will be giving one on Friday at 4. They'll be in the same place, the Mac classroom in the Science Center. That's Science Center 229. And the information is also on the website now, I think. So.
Yep, we'll post the information by this afternoon on the website, and there's also a solicitation to email CS50 plus RSVP again, just so that we have a sense of how many to expect. So as you know, by course's end, we'll be focusing on final projects, and we are quite fortunate this semester that Quincy House, by way of one of its tutors, is quite devoted to the idea of executing a great number of projects. And we have with us today Zach Stone, that tutor, to give you a teaser as to how you might get involved with Quincy House by way of your final project.
Hey everybody, I'd just like to give you a brief introduction to a really exciting category of final projects. As you already know, the goal of the final project is to benefit the community here at Harvard, impact the campus in some way. And I'd like to ask your help as a resident tutor in Quincy House to build an open source relative of Facebook that's customized for the Harvard houses. Now, most of you probably use Facebook at least once a week, maybe once a day. Some of you might be on Facebook right now. But as a house tutor, I can tell you that Facebook doesn't meet all the needs that the houses and probably the freshman dorms have here at Harvard. If you've ever tried to get to know your neighbors and look up your entryway on Facebook, if you've ever tried to figure out what your house tutors do, or the non-resident tutors, or if you tried to look up house floor plans or anything else, you realize that Facebook isn't designed to solve the Harvard houses problems. Now, last spring, I launched a new online community for Quincy House called 58 Plimpton, and the successes and shortcomings of that inspired me to ask for your help to build something larger, an open source framework to eventually replace all of the house websites with more useful online communities. So there are many directions this project can go, and many individual projects within it for a variety of skill levels. So I encourage you to get in touch with me, zstone at FAS, or through the course website to find out how you can get involved. Just as a taste, you can imagine having the house floor plans in a Google Maps interface with each room linked through to the students who live there. Or if you're in the river area, you can imagine ordering online from the Quincy Grill and having food delivered to your room. If you're interested in pre-law or pre-med, you can imagine looking at the profiles of the house tutors and non-res tutors who can help you with applications and internships and so forth. And there are lots of other projects that you can do. So I encourage you to get in touch. Please send me an email if you'd like to get involved, and I'll put you on the Google group where I'm organizing the project. Thanks very much.
So there are a great number of research areas and fields of interest within computer science: systems, theory, AI, graphics, programming languages, and a whole bunch more. And even the lines between some of those aren't even necessarily clear. So today we're going to give you a bit of a respite from hearing me speak. As part of a series of guest lectures we will try to do this semester from senior faculty within the School of Engineering and Applied Sciences to expose you guys to some of the different areas of computer science, directions you might go in future semesters, or really just to give you a sense of what there is in this world beyond what we do in this class. So I'm quite happy that our first such senior faculty member to join us is Professor Margo Seltzer, who was actually my undergraduate advisor way back when. She's here as a representative and leader of the systems group at Harvard. So without further ado, Professor Seltzer.
Great. Thanks, David. So this is a little bit of a homecoming for me. I've been at Harvard about 15 years, and the first year I walked in, Harry Lewis came by and said, "So what do you think we should teach in the first year?" And I thought about this a lot, and I went on for 15 or 20 minutes, and he said, "Great, why don't you teach CS50?" So for several years in the early 90s, I taught this course. I taught 51 for the last few years until I went away on sabbatical, and now I'm back and teaching other things. But I hope to see many of you in courses in your stay at Harvard. Those of you who are seniors, if I've missed you, well, come back to graduate school or something. So I'm actually not going to talk to you today about my research, because last week I was at a conference out in California, and it's perhaps, in my opinion, one of the best conferences. And I came back really, really jazzed about a couple of new topics. And so what I wanted to do was sort of spread the enthusiasm and energy that I came back with. So there were two things that really caught my attention. And one of them is the fact that we are all extraordinarily lucky to be doing computer stuff at the beginning of what is really going to be a revolution in hardware technology. And so what I'm going to do is I'm going to give you a little bit of a hardware talk to convey to you just what's going on, and then we'll talk about what the implications are for software, because they're enormous. And I am confident that the way most software is written today is going to be dramatically different from not so much the things you learn are going to be different, but the way that we structure programs is going to be really, really different 5 years from now. And so keeping that in the back of your heads as you think about what it means to do computer stuff will be pretty interesting. So without further ado, let's talk about hardware. So how many of you ever heard of Moore's Law? Good. All right. So Moore's Law tells us that the number of transistors that can be placed on a chip efficiently and inexpensively basically doubles about every 2 years. So who was Moore, and why should we pay any attention to him? By the way, those of you who haven't taken a course from me before, I'm very lazy. I make you guys do a lot of the work. So who was Gordon Moore? Yes?
He's the CEO of Intel.
Excellent. Good. That's the test to see who's awake. So he actually said this back in 1965. And if you know nothing else about technology, you know that every prediction that was made more than about 30 minutes ago is clearly got to be wrong and out of date, except Moore's Law. So this is actually a logarithmic graph of the number of transistors on regular processors starting in about 1970 and going up through the present day. And when you get a straight line on a logarithmic scale, that means that you've got exponential growth. And so, in fact, we're slightly under doubling every 2 years, but it's pretty darn close. And I think you'd be hard-pressed to find any other predictions about technology that have actually held for 40 years. It's really quite astonishing. So we're getting twice as many transistors on a chip every couple of years. So what? What are the implications of that? Anyone want to speculate? What happens when we can put twice as many transistors on a chip? Right? Transistors are what makes it go. Yes?
Able to do twice as many operations.
So you're able to do twice as many operations. Why would that be? Help me understand that leap.
Each transistor is sort of an on-off switch, and so the more on-off switches you have, the more control you have over what you're...
Good. So each transistor you can think of as an on-off switch. And if I have twice as many of those, then I can have sort of twice as many decisions. So I can do a lot more. There's another implication, though. The size of a computer chip hasn't changed all that much. So if I have twice as many transistors on a chip, what does that mean about their size? They have to get smaller. So if you have more transistors, you end up with smaller transistors. So what? Well, if I have smaller transistors, then the path between those transistors is also smaller. Okay, big deal. Why do we care? Well, what's the fundamental limit about how fast we can do stuff? Somebody here must have taken physics. Yeah.
The speed of light.
The speed of light. We're not going to change the speed of light, at least to the best of my knowledge. So if I can make the connections between those transistors smaller, then I can not only do I have more switches, but I can communicate between those switches more quickly. So as I get those transistors on the chip, I get greater speed. So you say, okay, that's kind of cool. Well, what has happened to speed as time has gone on? Well, so we've got the speed of light, but then as was pointed out early, we've also got more transistors. So you can do other things. And there are stuff like pipelining and caching and out-of-order execution that I'm actually not going to talk about today. But if those sound intriguing, then you should come back and take CS141 or 146, and you'll get to find out all about that. What I'm going to talk about today is ultimately going to be parallelism, right? So that's what's happening to our technology. And let's look at what happens to this speed. So each of these dots represents a processor. And what this is showing you is the clock frequency, or how fast those chips run. And it's not quite a perfect line, but you can certainly see the trend. And so clock speeds keep going up and up and up, and then somewhere in the middle, 2003, 2004, that trend is different. And if you're a technologist, you look at that and you say, huh, it's a little different. We know that the chips are still doubling number of transistors, but the clock speeds, there's something weird going on. Yeah?
What's the scale on the left?
So the y-axis is the clock frequency in megahertz. So 4,000 megahertz would be 4 gigahertz. Good question. If my students handed in a graph without a units, I would nail them on it. So thank you. So you look at this and you say, well, that's sort of interesting. There's something going on, and we want to understand that. So let's keep that in the back of our heads. But now let's look at performance, because that's what we care about, right? Clock speed is simply a stand-in for performance. So there's a standard way that people have been measuring processor chips for a couple of decades called the spec integer benchmarks. And this is a set of very small programs that you run, and you measure how quickly they run, and that gives you a unit of performance. And so now you feel a lot better, because you look at this and you see that sort of straight line going off to the right, and you say that our performance is still increasing. And that's good. But if our clock speeds don't increase, we're going to have to figure out how to get more performance out of our chips. So what do you do? If I can't just make everything run faster, what am I going to do? Yeah? I could put 2 processors on a chip. Now there's an interesting idea. Why would that be good? Yeah? I could do more than one thing at a time. Does anybody here do more than one thing at a time on their computer? Yeah? Okay, now I know that none of you do more than one thing when you're doing your CS50 homework. I understand that. But the rest of the time, you would never read email or IM or do any of those things while you're doing CS50. But the rest of the time, it's okay. I understand that you might do a couple of things at the same time. So let's see where this takes us. We got to figure out what to do with these transistors. And so what we're going to do is put more processors on. So this is a very simple picture of what a processor looks like. You've got a big chunk of the chip is called the execution core. And then you've got a bunch of different pieces of memory on the chip called caches. And the caches are usually arranged in a hierarchy. So you've got something called a level 1 cache. And then a lot of times you have a level 2 cache. Anybody know why you have caches on chips? Because the chip's just going to talk to memory. So why should I waste all those transistors putting memory on the chip? That seems like a silly thing to do. Yeah?
You can take out chunks of data at the same time. So if you read something and it's likely you're going to read something nearby on the hard drive or memory, and it moves it as a group, so you don't need to access memory each time.
OK, so it's moving data closer to the execution engine, and it's moving it as a group. That's absolutely right. So when I have data that's on my hard drive, I move it into memory. Why is it useful for me to move it from memory onto the chip? Why do you think? Yeah? OK. How fast is memory is the question. And the memory that sits on that chip is likely to run close to the same speed as the processor. And in fact, stuff that's in that L1, that pink cache, pretty much you can get a piece of data out of that every time your clock cycle ticks. So as your clock cycle gets faster, you can get data out of that L1 cache faster. The L2 cache usually is a little bit slower. Not too much, maybe a factor of 4 or 5 slower than your L1. Going to memory actually takes a long time compared to your processor. So the closer I can get the data to the execution engine, the faster I can go, and the quicker you can read your email. So this is all well and good. So that's how a basic chip works. What happens when we have all these extra transistors and we need to do something with it? Say, well, let's put 2 of them on a chip. So has anyone heard the term dual core or multi-core? So a dual core means that you have 2 of these execution engines. Usually, each execution engine has its own L1 cache, and then they share that L2 cache. So what do we think about this architecture? What are the first things that leap out at you? Can I get more work done? Yes, why? Somebody said the yes, now you got to come up with the second part. Good, so I can do 2 things at once, right? 2 cores are going to go together. What happens now if those 2 cores both need memory that's not in their pink cache? What do you suppose happens? Okay, so they want a piece of data. It's not in the pink cache. Where do they look next? The L2. But now you got 2 processors who are both at the counter saying, you know, give me that thing back there. I want it now. And you got 2 pretty grabby people standing here wanting the same thing, and you've only got 1 person servicing it, right? There's only 1 L2 cache there. So if you end up needing data there, now suddenly your 2 processors are kind of fighting for access to the L2. So when I put 2 cores on a chip, do you think you get twice the performance you got with the 1 chip? Did I hear a yes or a no? How many people say yes? How many people say no? Okay, so you're right some of the time. Those of you who would have said yes, you should have raised your hand because you're right some of the time too. Right? So it depends. And it depends on what you're actually doing. If you're doing something that requires a lot of memory out of that blue, if you're requiring something that requires a bunch of memory out of the blue stuff, then you're probably not going to get twice the performance. But if you don't need a lot of memory, then absolutely you can get all the performance you want. So this is a good strategy, and it's a good thing to do with these extra transistors, and it helps. Because as you all know, we're at least doing 2 things at once. So that's one way we can spend our transistor budget. Now let's look at another way to do this. How many of you have heard the term multi-threaded or hyper-threaded? Couple? Good. So we've got our same single chip system over here, single core system. And now what we're going to do, instead of duplicating the whole execution core, we're going to put a bunch of different execution cores that all share an L1 cache. And it turns out that when you do that, you don't have to duplicate quite as much logic as you do when you go to a whole other processor. So I have it shown here that you're really duplicating the whole execution core, but you don't have to duplicate the whole thing. So you can usually pack more threads on than you can cores. So now in this world, we've got 4 execution engines, so you can think of it as 4 programs running. But this time they're sharing both an L1 cache and an L2 cache. So what do you suppose the implications are for the performance of a system like this? Come on, somebody be brave. Nobody ever gives a wrong answer, so be brave.
They're not all running as fast as they would if they were by themselves.
Okay, they're probably not all running as fast as they would if they were running individually because they're sharing that L1 cache. Yeah?
Not all of them are going to be doing stuff all the time. Some of them might be waiting for bad hard drivers and things like that. So you need others.
Okay, but there may be times when there's nothing for one of those execution cores to do, so maybe it's okay. And the answer is actually a combination of all of these. See, that's why it was easy for me to guarantee that there were no wrong answers, because the answer is, well, it depends on what you're doing. So there are a bunch of different things that play into this. The way those execution cores are designed is they're designed so that if there's a delay getting to memory, it's hidden. And so what that means is that if we have 4 cores, so we have 4 cores right here. Okay, here are my 4 execution cores. So what happens is, when the first one requests a piece of memory, normally he would have to sit there and wait for it, because I would have to walk over here and get the memory and hand it to him. But instead of waiting and doing nothing and letting the hardware go idle, he waits for the memory, and now I go to my next core. Say, what do you want? You want a different piece of memory? I'll get that in a minute. And what I can do is I can sort of rotate through each of these cores and get them what they want, and I just have to have it ready by the next time I come back. And so this lets me actually use the memory that I have even more efficiently than I do when there's only 1 core. Well, I'm sorry, 1 execution core. So the hardware vendors are constantly playing this game, trying to figure out, how many of these things can I put together and get the best possible performance. And then they disagree, right? And Intel will say one thing, and AMD will say another, and Sun will say another, and it's great fun to sit back and watch, because we just get the benefit because the processors are going to get faster, right? And they're going to do more work. And not surprisingly, you can put these 2 things together and get multi-core, multi-threaded processors. So now, on a single chip, you can go out today and buy a chip that has 8 cores. I only show 2 here. Okay, so 8 combinations of green and pink. And within each of those green boxes, you get 4 threads. So those of you who are in higher level math, that's 32 threads that can be running at one time. Now that sounds pretty exciting. Right now, instead of doing 1 or 2 things at a time, I can do 32 of them at a time. This is great, right? So now you're a system designer, and you say, well, what am I going to use? What am I going to use all these threads for? I've got them at my disposal. This is so exciting. And how many am I going to have, like, tomorrow? Because if I got 2 or 4 or 32 today, that's pretty exciting. So here's a graph that shows what's happening today. Most of the chips are still down in the 4 to 8 threads. But Sun has been very aggressive on this, and they've got guys up in sort of 32. So far, we've only seen a very gentle increase here. But we're leveling off at clock speed. And what you're going to see in the next few years is that there aren't 10 threads on a chip. There aren't 32 threads on a chip. Within a couple years, there are going to be 100 threads on a chip. And if that isn't enough for you, within 5 or 7 years, there will be 1,000 threads on a chip. You're like, great. So if I'm building software, right, I can do all this stuff in parallel. This is fantastic. So I'm going to have thousands of cores. What am I going to do with them? And you scratch your head for a minute. I realize why this keeps going off. The power cord isn't in. So you scratch your head and you say, well, great. All the stuff that people do, they sit there and they do things at the same time, like read email and do your CS50. Oh, no, I'm sorry. Read email and listen to iTunes and watch YouTube and stuff like that. They can do in parallel. So that's cool. I'm going to be able to do more things at once. But the caveat in all this is that my single-threaded performance isn't going to get any faster. And you know what? It might slow down. Now, how many of you have ever gone out and bought a new computer thinking, oh, I got to get the new whatever because it runs slower than the old one? How many of you have ever done that? How many of you are ever likely to do that? Yeah, good point. So nobody's going to go out and buy a computer that's slower, or even that's the same speed, right? Why bother? You go out and buy new computers because they're faster or they have new features. So we've got to figure out how we're going to use all these parallel cores, because otherwise our computers aren't going to do any better. Now, if I'm doing 5 things at once and I have 5 execution engines, well, then that's good, because those should actually go faster because I'm not trading between them. So let's look at this do more things at once. So how many things do you really do on your computer at one time? Well, there's email and browsing and iTunes and movies and compiling and writing a paper and debugging and compiling and writing a paper and debugging and IMing and going and updating your Facebook page and also your new house page that will exist after the end of this semester. And you have to go do some shopping and get your books for next semester. And that uses up 8 or 9 cores. Even if you dedicated a core to each of those tasks, That would use up maybe 10. What do you do with the other 990 cores? We're not talking like you have 1 or 2 extra. You've got 990 extra cores in 5 years. What are you going to do with them? Who's going to go buy chips that have 990 cores that don't have anything to do? I don't think so. So we need to think of something else. We need to actually take advantage of the fact that we can do lots of things at the same time. Now, turns out that people have thought about this for a long time. Historically, the people who've thought about parallelism come from the scientific community. Why? Just because, like, they're geeks who like to think about this stuff? Why is it that people who've been thinking about parallelism have often been involved in the scientific community? What do those guys do? Any ideas?
Computations that are far too intensive to just sit around and wait for one core to do it for you.
Okay, so they do computations. And the thing they tend to do is they do computations on big data sets. Right? So for example, the human genome. Kind of a big data set, not a huge one, but the universe, really good sized data set. Or there are some folks at the IIC who have taken brain image scans at a resolution of, so they have each of the individual scans as a resolution of 1 cubic millimeter. And each of those is several gigabytes, because they slice these really, really thin and image them. And then they want to put them together and form a whole brain. Okay? So scientists have lots and lots of data. And fortunately, you can often take that data, cut it up into pieces, and process each piece individually. So for a long time, the scientific community has been very, very interested in how you parallelize stuff. And so the majority of all the work on how you parallelize things has come out of that scientific community. So that's good. So you say, good, let's just go take advantage of everything they've done and use it for what we do. Is there anything wrong with that logic? Right? They've already solved this. Can't we just use their techniques? The papers you write, you have several gigabytes of data for each of those, right? No? No? Anybody have an idea how big your paper is? A few kilobytes? 6 orders of magnitude smaller? Okay, so we probably can't parallelize that. Could, however, parallelize Skype. Sorry about that. Okay, so a lot of the data sets that you and I work with on our laptop probably aren't big enough to get a lot of advantage out of parallelism that the scientific community has done. So what else are we going to do? Well, there's some parallelism today in your applications. So has anybody here ever used Microsoft Word? Maybe? A couple? Okay, good. So, while you're sitting there typing your paper and thinking about writing the next great sonnet, Word has another thread that's going around in there and checking your spelling. And if you're lucky, your grammar, too. By the way, the little green lines are very useful. If they underline them, chances are you should change them, unless you're writing a sonnet, and then you might want to ignore them. So we do have parallelism in today's applications. Do you think we have enough parallelism to take advantage of these 1,000 cores that are coming? No. Turns out we don't at all. So what does this mean for you and us and people who are sort of thinking about what's going to happen in the future? Well, there are a couple things. So if you're thinking for like an economist, you say, for the last 40 years, computers have been a growth industry, right? They double in performance every couple of years. Even though they don't wear out for 3 or 4 years, everybody wants a new one like yesterday. So people buy lots more computers. We find lots more places to put them, and this is great. If you can't figure out how to exploit the new hardware, that is, take advantage of this parallelism, you don't have a growth industry anymore. You have a replacement industry. Right? So think about how often people replace their laptops versus how often they replace their refrigerators. Right? Refrigerators are actually not a growing market. Not a really exciting technology to be betting on. Computers, however, have traditionally been a growth industry. And in order to keep that up, we need to figure out how to solve this problem. So what does that mean for you? Well, on one hand, you could say it doesn't affect me at all because I don't need to write concurrent programs for 50 anymore. Is that right? Good. But on the other hand, it says there's this huge potential and opportunity out there. The world is changing, and it's going to change in dramatic ways. Most people today do not write parallel programs at all. Most people who write programs write sequential programs. 5 years from now, that's going to be different. Everybody's going to be writing parallel programs. There are two ways they might do it. One, they might do it because the tools just make it happen magically. Or two, they might have to think about it. And three is it's going to be a combination of the two. Right? People have been trying to develop tools for the past 20 or 30 years to figure out how to make things happen in parallel. And they've made small steps. They're going to have to make bigger steps. And we're also going to have to figure out how to start designing programs so that they can run in parallel. So this means that, if you're worried that gosh, writing a program, it's just not creative enough, there is room for tons of creativity here. Because we're going to have to think differently about how we solve problems 5 years from now. And the tools that you're learning now are exactly the tools that are going to let you do that. Right? Let me be clear. It's not at all that what you're learning now is going to be irrelevant. Absolutely not. All the problem solving and design skills that you develop now learning how to write programs are going to be even more valuable next year and the year after and 5 years out from now. So, how do you take big tasks and break them down into little tasks that can happen in parallel? Well, it requires a different way of thinking. What languages should we use? So there are raging debates about how we're going to get all this parallelism and what languages are better than that. If you stick around and take 51 next semester, you'll learn a language called Scheme, which is called a functional language. And there are people who believe that functional languages are going to be much easier to parallelize. And there are good reasons why they're easier to parallelize. So maybe we'll see more functional languages. Maybe we'll see more people learning those. I can't tell you. I'm not going to look into my crystal ball and tell you how we're going to solve this problem. But what I will tell you is that there's going to be a whole lot of energy and creativity focused on trying to tackle this problem because the impact is huge, huge, huge. And if you can sort of just conceive of what it's going to be like, 8 years from now when you have 1,000 concurrent things happening on your computer at one time, I would hope that that's enough to at least wake you up at 11 o'clock in the morning, if not get you really excited. So that's what's happening in software. And, I've been thinking about this a lot and trying to figure out how do I change the way I build things so that I can take advantage of this. And if you come and take more courses with us, you'll get the opportunity to do that as well. So that was all I had that I wanted to talk to you about, but I would love to take questions. We can brainstorm a little bit about how, all of us in this room are going to solve this problem by Wednesday. Or I think other than that, they get out early, right? Yeah, so we know how energetic this discussion will be. So come on. Questions, comments?
Seems like we had dozens of processes or dozens of industries that meet other secondary problems. So how do they solve that?
So that's a great question. The question is, if we keep putting more transistors on chips, we introduce other problems, and in particular, one we generate is heat dissipation. Right? Every transistor gets hotter. So there's a parallel. So you're absolutely right. As we put more transistors on the chips, they get hotter. So, and I couldn't have paid you to ask a better question, because this actually will let me talk about the other really cool thing I was exposed to last week. So if you look at how people build data centers today, they build these things called 1U boxes that fit in racks. And each one of those has something like, a hot Intel chip with a bunch of disks. And they consume an inordinate amount of power, and they're hot. And so you build air conditioning in. And the majority of the cost in a data center is the energy to run the processors, and then the air conditioning to cool them down. You think about that for a minute and you say, gosh, isn't there a better way? Now, turns out that this annoying little device that rang a few minutes ago has a 32-bit processor in it, fair bit of memory, but when I put it in my pocket, it does not burn a hole in my leg. And the people who build these devices think that's a good thing. I think it's a good thing too. So how is that? Well, the processors that they use in cell phones and most consumer electronics are low power devices. So instead of consuming, 20 or 30 watts, they consume about a quarter of a watt. You say, yeah, but those aren't real processors, are they? Well, there's ARM processors today that are a gigahertz, pretty darn fast. It's not the 4 gigahertz of today's fastest chips. They have somewhere between 128 and 256 megabytes of memory, which maybe doesn't seem like a lot when you're looking at 2 gigabytes on your laptop, but I got a secret to tell you. 5 years ago, we thought that was enough memory. Don't tell anyone. So suddenly what you can do on a board that's about the size of a stick of gum is you can build a processor that's comparable to, a PC from about 5 years ago. Well, that's kind of neat. Oh, and by the way, it consumes 1 watt of power. So instead of building these 1U boxes with, a single Intel chip and a bunch of disks, I can take 124 of these little gum sticks, mount them vertically on this board, and now I have an amazing amount of computing power and memory and everything else. And oh, by the way, the whole board's only 120 watts, and the heat dissipation is perfectly uniform across it. There's no heat sinks, there's no fans, and there's no need for humongous air conditioners. So in terms of what's happening is you see the low power guys building these ARM processors and stuff like that, and you see the big chip vendors going and building hotter and hotter chips. And so there's a real question about what's going to happen. And my prediction, which I won't put any money on, is that you're going to see computing start to move over to these low power chips because it's a whole lot cheaper. I can run my data center at a fraction of the cost, but what's the problem I have to solve? Let's think about it. I got 120 processors on this board, and I want them to solve problems. What does that sound like? Doesn't it sound like the same problem I've been talking about, that you've got hundreds or thousands of threads running in parallel? So the exact same technology that's going to let me solve this core problem is going to help me solve the power problem, because I'm now going to run on lower power chips and use more of them. So that's my prediction, is that the guys who are doing low power are going to win ultimately. And you will see, and in fact, if you look at Intel and AMD and those guys, they're starting to introduce low power chips. And my prediction is that they have to do that because eventually the low power guys will win. It's just too economically desirable to solve the heating problem. Does that sort of answer the question? And that was great, because these millicomputers, so if you go to www.millicomputing.org, it's a bunch of guys. This is the Homebrew Mobile Computing Club, which is sort of the current day version of the club that Steve Jobs belonged to when he started building Apples. And these guys are off trying to design millicomputers and figure out how to solve various problems and buy these gumstick computers, and it's a blast. So go check it out. It's really fun. Any other questions? Yeah?
You didn't talk a lot about single thread advancements, or you said that you didn't foresee it a lot. But what do you think about spintronics?
About what?
Spintronics?
Spintronics. I know nothing about spintronics, so educate us a little bit.
Just the idea that it takes less energy to change the spin of an electron rather than today's computing.
Okay, so right. So there's the question of whether we'll find new technology that will let us sort of get back on Moore's curve in terms of performance. And I think the jury's still out, is the answer. I think there have been, gallium arsenide was a really, really hot technology about a decade ago, and this was going to solve our problems, and it didn't. And so right now, everybody's betting on multi-core. And if somebody can make it practical and real, then we'll see another interesting debate play out in the market. But for now, that doesn't look like, they just don't know. Other questions, comments, solutions to this problem? If you have solutions, speak up now. We can go off and make people not worry so much. The top people in the field are really worried about this, both from a technology standpoint as well as an industry standpoint. Yeah?
Why do we need to make computers that much faster? Like, is there a point that we reach that we don't need to have computers that fast?
So that's a great question. Why do we actually need computers to be that much faster? And the answer is multifaceted. So one answer is the economic one, which is that let's assume for a moment that we have nothing to be done with faster computers. And let's run the thought experiment. What that says is that the whole computing industry will change from a growth industry to a replacement industry. That has enormous ramifications on the economics of companies that depend on high tech, right? Because the replacement rate is much, much lower than sort of the growth rate. So it's possible from a technology standpoint that computing will become just like other replacement industries. You know, the automobile industry to a large extent is a replacement industry. That would have an enormous economic impact, right? And we're seeing today, in some sense, the economic impact of that having happened in the automotive industry. And it's had a big impact in this country. So people are afraid of that from an economic point of view. And then there's the other side, which is that historically, whenever we've come up with better and faster computers, we've invented new cool things we could do with them. And so if we stop doing that, then we may be shutting ourselves off from a whole other branch of creativity about what we could possibly do with computing. And given the success we've had there, it would be a shame if we didn't get to keep going and see what else we could figure out what to do with computers. So there's a real intellectual fear there as well. Other questions? Yeah?
To what extent in the desktops or laptops you buy today is the bottleneck the processor and processor speed or the other components?
So the bottleneck today is what they call the memory wall to a large extent. So you've got enough main memory on your computer that you can get most of your data in there. You don't wait for disk a lot. There are a few cases where you still wait for your disk. The real bottleneck is how quickly you can consume the data, because those caches, they just aren't that big. So one of the problems is the mismatch between the processor speed and the memory speed. Say, okay, so maybe we don't have to make faster cores, and that's good, because we're not making faster cores anymore. Now you've got a different problem, which is how do we break this memory bottleneck? And there are people out there with competing technologies. Memory is a very, it's a commodity market, and the companies, you know, it's not that they collude, but they're very conservative. And so getting them to adopt new technologies is actually really hard. And so there's tension right now playing out in that memory arena. So I think what's going to happen is that when somebody can really demonstrate that they've got something that's going to break that wall, then the memory industry is going to sort of go into chaos for a while and try to figure out how to respond. But that's probably the biggest problem facing, you know, desktop performance, is that memory wall. Other questions? All right, then it looks like you get out a few minutes early. Any announcements?
Please come down to chat with Professor Seltzer if
You
you'd
bet.
like afterward.
You
See
bet.
you Wednesday.